In the last video we looked at the idea that work caused a change in energy, and the amount of work was based on the amount of force acting in a certain direction. So the last example was this one here, where you get 120,000 joules of work being done by multiplying those two quantities. So it's force times by displacement. You can also do the same thing with dragging a crate across the floor, or pushing a crate across the floor against a friction force. So let's say we're going to move at 5 meters against a friction force for the crate of maybe 100 newtons of force there. So you would need to actually push the crate forward with a force against that at a steady speed of the same amount there. So we're going to use force times by displacement there still. So the force you're going to apply to overcome friction is 100 newtons to the right there. That's going in the same direction as the displacement of 5 meters, so the two are going in the same direction. And the overall work done then is going to be 500 joules of work, which of course is the energy that's going to be produced there, or used up or changed by that process. If you had a slightly more difficult question then, where it was going to go upwards and we were going to lift the object there, similar to the last one, but this time you do not know the force that you're pushing against, you need to work it out. So this time I'm just going to tell you the mass is 10 kilograms rather than the actual weight or the force that we're trying to pull up against. So here we're trying to lift it to the top of that table, maybe 1.5 meters high. And if you do that there, we're going to use that same formula, work is force times by displacement. So the force in this case we need to work out. We know the displacement. So we're going to move up against the weight here. So weight's actually a force based on F equals ma. So what sort of weight does it have going downwards at the moment? You would look at mass times by acceleration, or mg is the other formula you can use for this, which would be 10 times by 9.8. So it's got a weight of 98 newtons, so this time you have to work it out, and therefore you would know how much force has to act upwards. So 98 newtons upwards, times by 1.5 upwards, the total work done to lift it onto the tabletop would be 140. It's actually 147 joules, but I haven't got my eraser there, so it's 147 joules. Next sort of one you can do with this would be something along the lines of, so that's the crate one. You could do, consider that's going to change the potential energy then, so that's going to gain potential energy there. So the amount of work done causes it to gain potential energy to the top of that object. So in this case, you could also work out a potential energy formula that's been given to you, where the mass is important, how high it is off the ground is important, and obviously the gravity is important, depending on the planet you're doing it on. So looking at that there, you would do a similar sort of set of calculations using this given potential energy formula. It's mgh. So that's the other sort of formula you can get. So in this particular one, let's give it a height of, say, 10 meters, and we'll give it a mass of 2 kilograms. So in that case, you've got 2 as a mass. It's on planet Earth, so it's 9.8, and you've got a height of 10 meters. We're going to lift it up there. So the potential energy when it's sitting on the top then is 196 joules. And that's very much the same sort of thing you get if you were to go work out the work to lift it to the top here, because the work done to lift it to the top has still got that same definition of Fs, or in this case we will break it down to MAS because we don't know the force at the moment. We have to work it out as MA, and we're going to have a mass of 2 with an acceleration due to gravity of 9.8, that'll tell you the force, and then you times by the height you're lifting, which is 10, and of course you get the same answer, 196 joules, because the work done to lift it up to the top of that object, that cliff there, is going to convert it to potential energy. And we've already got a potential energy formula, and naturally the two match here. So just bear in mind that potential energy formula there has come from a work definition initially. The idea that work was MAS was your starting point, and they've just substituted that into GH to try and actually give you the idea of a potential energy formula that you could use all the time as a standard. So displacement is going to be height, and the gravity is the acceleration due to gravity there. So there's your two substitutions. So that's an easy way of getting potential energy, and it's obviously coming from the work formula. So just keep that in mind, and that's the change in energy, which is that delta symbol you'll sometimes see in the books as well. So thanks for that.